Good afternoon, everybody. Welcome to this session of sustainable construction methods. Today, we'll be seeing this topic: concrete and steel bridges. What are the different types of these bridges, and how are they designed, and what is the importance of each and every bridge? We'll be seeing that today. Let us start with it. Steel bridges. Let us see what are the advantages of steel bridges. They have high tensile and compressive strength. As you can see, there are the different types of loading come onto this bridge, so they should be able to resist this loading which comes onto the bridge. So they should have high tensile as well as compressive strength, so that it can resist the loading coming onto it. You see, it has high strength to weight ratio, low self weight, and less loading on substructure. What happens, because it is made up of steel, it doesn't have that much load, it doesn't have that much of self weight, while whereas compared to RCC bridge, reinforced concrete bridge, so it doesn't have that much load. So the weight load is also less, which is transferred onto the substructure. You can see it is uniform. Also, you don't find uneven surfaces also, because all these steel structures are already, they are prefabricated, they are made in the industry, and just they are transported to the place as per our requirement. So it has uniform, also high quality material. Material can be maintained. The quality of the material can be maintained, as it is designed in a closed environment where there are no chances of deterioration of material. Also, speed of construction. Construction is also, the speed can also be increased. The on-site construction can happen at the same time, as well as the off-site construction. The steel members which are to be casted later on can also be prepared at the same time, thereby reducing the time. Versatile. You can see versatility of the construction. It is very easy to construct. Also, there is not much complications also in construction of these type of steel bridges. Elasticity, it follows Hooke's law very accurately, where Hooke's law, as we know, the stress is directly proportional to strain. Under the so stress and strain are directly proportional to each other. Ductility, it can withstand high deformations before failure. It gives a warning before failure. It is ductile in nature also. The steel bridge is ductile in nature. It already gives you warning before the final collapse of the structure. As you can see, before the failure, the steel bends and gives you a warning that it is about to collapse. So you have chances to save the structure also, as well as other things also. Modifications can be made very easily. Strengthening of the beams. So modifications can be made easily also. You don't require much of the problem also. You can just see here stress strain curve for the concrete. You can just see here. Uh, as we know, the stress strain curve, we have been seeing this from past many classes, or last year also in strength of materials also you have seen this curve of stress strain curve. Yeah, and Hooke's law said that the stress is directly proportional to strain, and after that what happens, there is a elastic deformation also takes place after the loading increases. Even this happens after some time. You can see here there is compression and tension also. Here at the top it is tension, and bottom it is compression. Stress is directly proportional to strain. You can just see a short term design stress strain curve for reinforcement. What happens as the load increases, there is strain also. As the stress increases, there is strain also. But once the load is removed, the material comes back to its original position. Within the elastic limit, stress is directly proportional to strain. But after some time, what happens if the load increases? Then after the elastic limit is crossed, then the plastic limit comes, where the failure starts place from there. The first failure starts place from there. So what are the disadvantages? See, why don't we adopt steel construction everywhere, or steel bridges everywhere? There are some disadvantages also related to these steel. Maintenance cost is very high, corrodes when exposed to air, water, and humidity. So this is the biggest problem. What happens is maintenance is very high, as steel corrodes very easily when exposed to air, water, and humidity. So we need to keep maintaining this time to time. If this is not maintained time to time, there is high amount of corrosion takes place, thereby leading to collapse of the structure. Fireproofing cost reduces at high temperatures. At high temperatures, strength is reduced. If there is some high amount of fire due to some any untoward situation, at those time also it is not able to resist that fire also. So this is the problem with the steel construction. Susceptible to buckling, slender structures. There are chances where the structure can buckle down. It can collapse because of the axial load coming onto the structure. There are chances of vertical members getting buckled there. So it should be proper care should be taken where these vertical members should be provided with some stiffness so that they don't buckle down. Fatigue strength reduces due to cyclic loading. Continuous loading, cyclic loading is a continuous loading one after the other. Because of that, there are chances of the strength getting reduced one after the other. Types of steel bridges. Let us see what are the different types of steel bridges here. We have beam type steel bridge. We have girder type of steel bridge. Beam and the girder are the same. Girder is that beam which is very large enough. Simple beam. A girder is also a beam, but it is called as a girder when the beam is very large enough. So we have truss girders, truss steel, truss bridges also. We have plate girder bridges also. We have box girder bridges. We have cantilever bridges. We have arch bridges, cable stayed, suspension bridge, and mover bridges also. Or these are the different types of bridges what we have. We have temporary as well as emergency bridges also. You can just see here beam on the girder bridge. You can just see this figure. You can see the what you can just see the length of the beam, how long it is, what it is giving a very big passage at the bottom for the traffic to flow on without uh, giving a free passage to the traffic to flow on. So this is a beam type of bridge, beam type bridge or a girder type of bridge. You can just see here the columns have been raised and the abutments have been casted on side. Over that, a steel bridge of a beam girder bridge has been casted, has been erected there, and welded or bolted depending on the need or depending on the whatever calculation what we are using. It has been bolted and fixed there, and after that, over it, you come up with a small concrete or a flexible pavement structure over it. You can just see rolled I sections are used as a main support. Rolled I section. They are I section. You can just see this. You can see these are I section which are placed over over this girder, over this support. These are the I sections which have been placed, and these are the bracings which have been given at the bottom. Bracings have been given also so that there are no chances of any buckling also. So these are the huge I sections. You can see other members, cross girders, stringers, deck bracings. As I told you, bracings are also there, which can be seen there. Two beam girder system or multiple beam girder system with cross beams even. So depending on the need, two beam girder system also is there. Two beams. We have already four multiple beam girder system. We have four beams here and four beams or four girders here with cross bracings also provided at different intervals. Cross girders. You can see here these are the bracings which have been provided here. So this is the beam girder. Let us see the truss bridge. Truss bridge. You can just see this is the truss which has been connected, which has been rested from this place to the other place. This is the truss. You can just see this truss how it has been formed. You can see vertical members as well as horizontal members, and cross bracings also have been provided so that the load can be distributed equally and it is not only onto the horizontal members only. Different truss types you can see. We have Pratt truss type, we have Parker, we have K truss type, Hovey, Camelback, and Warren truss. Normally these are very much used. Warren truss and Pratt truss are normally very much used. You can see Fink and double intersection point also. All these depending on the load coming onto the structure, these type of truss are decided or finalized. Warren with verticals, you have Warren truss with vertical members also here. You have bowstring also, Baltimore double intersection Warren. You have Waddell A truss, Pennsylvania lattice. So depending on the load coming onto the structure and what are the different wind loads or whatever loads coming, we'll have to finalize with what type of structure to be taken. Types of truss bridges you can see. If the deck is located at the level of the bottom chord, the bridge is called as a throw truss. Throw truss. If it is at the bottom, you can see the deck is located at the bottom level of the chord. Bottom level of the chord, then it is called a throw truss. You can see here a pony truss looks just like a throw truss, except it is not as high and has no lateral bracing between the top chords. You can see there is no lateral bracing here between the top chords, and it is not so high. It is not so. You can just see this is very high here, throw truss, whereas this pony truss is not so high. You can just see here. It is resting at the same way. It is resting same way. You have these bracings here, but it is not so high here like this one placed here. If the deck is located at the level of the top chord, the bridge is called as a deck truss. You can just see it is an inverted structure You can just see the structure. It is an inverted structure with the bracings provided at the bottom, and you can see the free flow of traffic from here. So this type is the deck truss type. You can just see here what is the level of bottom chord. Depending on that bottom chord, this is how the trusses have been differentiated. Truss type, truss bridges, you can see it can be used for span up to 200 meter. It is possible 200 meters. It is structurally very efficient also. Reduce self weight. It doesn't have a lot of self weight, thereby reducing the weight coming onto the bottom substructure. Several type of truss arrangements possible are Warren modified, Warren Pratt, Fink, Hovey. So normally these type of truss bridges are used normally this type. You can just see a components of a truss bridge. You can just see it. Don't get confused here. Upper chord transverse bracing. Upper chord transverse. This comes on the top. Upper chord transverse. Upper chord bracing. It is a slant bracing. Slant bracing. This is transverse. This is horizontal. This is slant bracing. This is the upper chord here. This part. This part is the upper chord here. Then you can see end post. This is the end post. This is where the bridge is ending. Vertical members. These are the vertical members. You have diagonal web members. Diagonal web members to support and to reduce the buckling. So this is how lower chord. This is the lower chord part. Now this, depending on this lower chord, only the different types of truss have been differentiated. Lower chord bracing. At the bottom you have bracings also. You can just see at the bottom you have bracing. Floor beam is there. Stringers are there. Also all these make up a truss. All these make up a truss. This is how the truss is designed. You can see Warren truss here, Pratt truss here. Warren truss, you can just see how it is placed here. It is placed on hinge structures here. It is resting a Pratt truss and the Warren truss. Equal length members, easy fabrication. You can just see it is economic. It is economic. Pratt truss variant is a longer members in tension, slender diagonals are possible, efficient structure. Even this is an efficient structure. So basically these type of trusses are used. You can see a plate girder bridges. Plate girder bridges, we had seen this subject in our previous classes, previous subjects also. Plate girder, how it is designed. These are the vertical, you can see a vertical members and horizontal members, and the rivets being used to connect these members. You can see these are intermediate stiffeners. These are intermediate stiffeners. And this is the I section. This is the I section which is connected with the intermediate stiffeners. And required, if required, you can provide horizontal stiffeners also as per the need and the load coming on it. Box girder bridges, you can just see here. This part is the on-site construction. This column and this support, or this support is the on-site construction. And over this, a box girder is being placed. A box girder is being placed with the support here. Just see here, very high torsional rigidity. It has very high torsional rigidity, also torsion, where the torsion is that property where you can the structure gets twisted, or the member gets twisted the same way, the way we twist a towel, that is, or we how we twist clothes to dry them up. So this is what is torsion. The very high torsional rigidity is there. Effective use of construction materials. The construction materials can be used very effectively here. It is possible for longer spans also, longer spans. But complex execution is a little bit complex. You need very skilled laborers here for box type of bridges. Skilled labor is needed here. Cantilever bridges, you can see here cantilever bridges. You can just see here back span. This is the back span. This is the main span of cantilever bridges. You can just see here from this part a cantilever is fixed till here. From this part a cantilever is fixed till here. Between them this type suspended span. Cantilever arm. You can see this is the suspended arm which is attached because of these cantilever arm. You can see here this is the anchor arm or back span. You can just see the structure here. But this is the cantilever bridge. This is designed as per the need whenever we need. Cantilever bridges permits a longer clear span for navigation. You can see here we are getting a very clear span for navigation here. Just see this, such a big span is there for navigation, whereas here you don't get that such a big span. Because of this cantilever bridge, this is possible here, a big span. Main structural elements are anchor arm, cantilever arm, and suspended arm. So these are the main structures: anchor arm, suspended arm. You can just see here anchor arm. This is the suspended span and the cantilever. These are the main structures which connect to each other and thereby forming a cantilever bridge here. Arch bridges. You can just see here, these are the arch bridges. You can just see this arch here placed over it, and over this, these structures, vertical structures have been placed, and you can see the traffic flowing from here to there. You can see this. You can see this vehicle. You can just see this construction, how marvelous it is. It is being connected from one mountain to the other mountain. It has been connected. You can just imagine how this structure had been casted here. Just imagine how difficult it would have been, how slowly, how this calculation would have been done, how this arch would have been formed, how the loads have been distributed evenly. Because here, because in the middle for the arch, this is the highest load coming here. So there you can see arch has been formed, and thereby when you move at the corners, the loads keep decreasing here. So arch bridges, you can just see this arch here also. It is marvelous construction here also. This is in Australia. Opera House can be seen here. You can just see the arch bridge. Arch bridge. Very good construction here. Arch. Structural action similar to old masonry arches, bending moments much lower than in typical bridges. So bending moments are reduced because of this arch action. Bending moment is reduced here. Deck support, hangers or struts, depending on the need, hangers or struts are used at the corners. Cable straight bridges, you can see this is the marvelous construction which have been taking place in the recent times. Cable straight, all this have been you can see these cables here hanging from here, and all this whole bridge is being the load of the coming onto that bridges is being taken by these cables which have been suspended from these pylons. From these pylons, how this cables are being suspended here, they are holding this bridge intact, and thereby giving a very good space for navigation here. You can just see how good space is given for navigation here, and these are the cables which have been holding this bridge here. You can see span 200 to 500 meters. This can be built for a span for 200 to 500 meters. Main structural elements are cables, towers, that is pylons, and the deck. So these are the main structural elements. 200 to 500 meters. You can just imagine such a huge span can be made during using the suspension bridges. You can just see here suspension bridges. From here, these are the cords which have been suspended here. There's a these have been suspended here, and thereby this load is being taken up by these cords, and they're transferred to these bridges over here. It is being transferred here to these bridges. You can just see this construction. It is marvelous construction. It is being suspended by these cables here. You can see just spans excluding 600 meters. So suspension bridges can be used for spans up to 600 meters. Main structural elements are flexible cables, towers, that is pylons, anchorages, hangers, and the deck. So 600 meters is a very big span, and the main structural elements, as you can see, cables, towers, anchorages, hangers, and decks. It is light and strong, very expensive. The only problem with this is it is very expensive. It is light and strong and very good. Movable bridges, you can see a movable bridges. They have been constructed here as per the need. You can see the ship is being is coming crossing over here. At that time, these bridges will be moved away. It is they move away. These bridges open up and they give way for the ship to move on. You can see in the next figures here. You can just see here movable bridges. It is a very good construction here. It is being connected whenever there is no need for this to open up. Here they are connected, and the traffic flows from here to there, and thereby whenever need is there, this bridges are being opened. You can see a ship is coming here and there, and these bridges are being opened where the ship can pass. Permits passage for navigation by moving, swinging the bridge deck when it is either impractical or too expensive to provide a bridge with sufficient vertical clearance. So this is done when there is impractical or too expensive for the vehicles to cross over a long distance. At those places, then this type of movable bridges are being used, where there is a lot of navigation activity as well as road activity also. Then at those places, these type of movable bridges are constructed. Moving action, left sink or swing, depending on it either sinks or it moves up and down. Temporary and emergency bridges, you can just see a simple bridge where it has been constructed for temporary construction, where just to give a passage for these water to go away, and passage for any activity to perform here. You can see here this simple emergency bridge has been constructed here. Simple emergency bridge with bracings and all, and it is providing supporting. It provides support. It is resting here. You can see here it is resting here, and here it provides support, and the traffic can flow from the top of it. See, temporary bridges, just as per the need, temporary bridges is being erected here, put here, temporary bridge. Once the need is over, it can move away. You see, it is fixed to the tank here, fixed to a tank, and there a temporary bridge is being laid there. So erected within a very short period, that is only within a 1 day, no permanent abutments or piers, nothing is required here, specially provided during wars and after natural disaster. During natural disasters also what happens is the bridge links and everything are being broken or collapsed. At those places we require some emergency bridges to reach the situation where the disaster has happened. Let us see concrete bridges. Till now we had seen the steel bridges. Let us see the concrete bridges. What are the advantages of concrete? Ingredients of concrete are easily available. Everything, whatever the materials required for concrete bridge design are easily available anywhere. Unlike natural stones, concrete is free from defects and flaws, faults, joints, stratifications, etc. So what happens is different stones have different properties, and there are chances of various faults and joints coming into those stones. But in concrete, what happens after the mixing and placing of the concrete, it becomes so hard, and there are no chances of any faults or joints coming onto that concrete. Concrete can be manufactured or designed strength with economy. So desired strength can be achieved with the economy also, maintaining the economy. The durability of the concrete is very high. It is very high and durable also. It can be cast to and any desired shape. It can be casted into whatever desired shape we require as per the need and the shape. It can be casted. Casting of concrete can be done at work site, which makes it economical. So at the work site also it can be casted also concrete. Maintenance cost of concrete is almost negligible. Unlike steel bridges, where the maintenance is very high, but in concrete bridges you don't have maintenance of that amount. Disadvantages of concrete compared to other binding materials: the tensile strength of concrete is relatively low. See the tensile concrete is weak in tensile, in tension, and good in compression. So concrete is less ductile also. The weight is high compared to its strength. So yes, the weight is very high where compared to its strength. The self weight is very high, whereas if you compare to the steel structures. RC bridges suitable for small and medium span. For small medium span, reinforced concrete bridges can be used. Special requirements: restriction on provision of formwork construction period. Yes, the formwork and construction should be done at a very short period of time, because the traffic or the navigation can't be stopped for a long time. Most of highway bridges are reinforced concrete bridges. Several types are available: slab type, beam type, box girder, continuous girder, balanced, cantilever, and arch bridge also in concrete. Let us these slab bridges. You can see this figure here. Slab bridges. These are constructed at the bottom. This abutment and piers have been constructed, and then this slab is being pre-casted and just is got onto the side and casted here as per the requirement. It is casted here. It is not done on-site construction. Slab bridges, you can see RC slab serves as the main superstructure member, requiring no other beams or girders to carry the loads. Not suitable for larger spans since the slab becomes thicker, increasing dead weight. You can just see it is so thick, so it doesn't require other beams or girders to take this. It is very thick, not suitable for larger spans since the slab becomes thicker, increasing the dead weight. So it has very high self weight or the dead weight. Therefore, it is not good for larger spans. It is economical, simple design, solid hollow slabs. It is economical. It is very easy, but still it can't be used for larger spans. Beam bridge. You can just see this beam bridge. You can see this beam bridges have been casted here. Over this, then a small slab bridge comes, which is being casted here. You can just see the reinforcement being placed. These are casted prefabricated or pre-stress concrete structures which are made in the industry, and this it is got onto the site and assembled here. Beam bridge. RC beam, reinforced concrete beam, serves as the main superstructure member, widely used due to simplicity, economy, wide availability of the standard section, and speed of erection. As I told you, it is erected beforehand in the industry and just got onto the side and erected there. Precast beams are placed on the supporting piers or abutments, usually on rubber bearing, which are maintenance free. What happens? These precast beams, they are first put onto the abutments with the support of rubber bearings. Now, what type of beams are used? I beams are used. A deck is constructed on top of beams spanning between the beams. Yes, once the beams are being placed, then the deck is being constructed over it. Box girder bridges for spans greater than 45 meters. So box girder can be used for spans greater than 45 meters. Pre-stressed concrete box girders are the most common method of concrete bridge construction. Like precast, pre-stressed concrete box girders are already made and they are got onto the site and they are fixed there. Box girders are fixed there. The main spans are hollow and the shape of the box will vary from bridge to bridge and along the span, being deeper in cross section at abutments and piers and shallower at mid-span. So it is deeper in cross section at the abutments and it is shallow at mid-span. Incrementally launched, it is span by span balanced cantilever. So all this is there with box girder. You can just see here box girder. It is got onto the side and just fixed here one by one. It is resting onto the abutments with this. You can see here rubber elastic members here on over it. It is resting. You can just see this bridge design. Bridge design will be taught later on. Also loaded length. What is the amount of length here loaded? Normal loading. You can just see what are the loading coming here. So this is the loading for 3 meters. We have 9 kilometer per meter square, and for at the between you have 2.5 kilonewton and 2.5 kilometer. Lane 1, lane 2, lane 3. Basically, we are seeing what is the highest intensity of load coming onto it. So this is as per the European code. Influence line diagram, you must have seen here influence line diagrams, how you can see influence line for bending moment at support 3, at support 2, you can see this bending moment influence line diagram. You can see here for the mid span also, you can span influence line for the bending moment mid span of section 2, 3. Typical influence lines for bending on continuous decks. In continuous deck, you have this influence. Where is the highest intensity coming? There you can calculate. Influence lines you can see here for a force in member A. In member A, what is the force here? Here also it can be calculated. Bridge deck design, we have seen this design of deck slab also in the previous classes, so it is not much of importance here. You can just see the loading coming onto it, how the axial loading is coming, how these abutments takes this type of loading, and what is the maximum bending moment coming onto it, that will be seen here. You can see here this the loading, how the loading is come, and what is the distance between these abutments, 1000 mm, 2000 mm to 2 meters. That is how these are the different spacing between them. Because of this, you are getting a clear span here. Just see here the load coming. Stresses in plate girder, how the stresses are being distributed. You can just see the stresses how they are distributed from the top and the bottom, which had been calculated beforehand also. In the box girder also, what are the stresses coming here? The box is being formed here, box girder type, how the stresses are being formed here. You can just see here how the stresses, horizontal and the vertical stresses coming onto this box girder can be seen. Bending of box girders, how they bend. You can see a loading in vertical plane also, how the loading is there. Then you can see the loading in horizontal plane, bending stress vertical plane also. You can just see this, how the bending moment diagrams and everything are here. You can just see how the loading takes place. Finite element analysis, basically nowadays all this is being used using the software, and it is all this is being distributed into small finite elements, and each stress coming onto those elements are being calculated or checked. Finite element analysis, you can see here this whole structure is being uh, the whole structure is again it is made into small strips or small boxes, where the stresses into each box can be calculated very easily. This is finite element analysis. You just see everything nowadays is being calculated using the finite element analysis. Into specified structures, you can see it is square or a rectangle or a circle only. In this one you can see typical example of finite element: mesh, slotted lip channel, plate girder, curved and plan, steel, concrete, composite, plate girder. So this is how it is mm, uh, it is being distributed in different small structures, and there we see what are the different types of stresses coming onto each small box, you can see. So for this, thank you for today. I request all of you all to go to this session, and please comment in the comment section. Thank you.